thanks for your introduction. This is the outline of the presentation. I'll discuss the three-phase flow model, and in particular with some results for two-phase and the case of balance loss with the interface. I'll discuss a little bit the computational method, some numerical experiments, and some conclusions. So first of all, I'd like to thank many thanks, to the main organizers of the workshop on Porous Media here, the funding agents, and with a special thanks for some people, in particular Professor Felipe Pereira, Fred Furtado, Dan Marchesin, and Jean Douglas. I like to give my special thanks for all of these people that helped a lot and for their support for all the times. So the focus here is related to the INTERPORE activities, and for the computational point of view, I'm interested in the numerical simulation of transpose phenomena under discontinuous hyperbolic parabolic flux functions. And the motivation, as previously discussed by many speakers, is the wide range of applications of multiphase flow in porous media, from science and from the natural science point of view and engineering point of view. So we can skip this, some basic and standard kind of applications to the porous media. And of course, our interest here in Brazil is the so-called the pre-salt basins. And we are interested in such kind of possible applications to this for Petrobras. So we are dealing with a very simplified model for the engineering point of view. It is a three-phase flow model. We neglect the mass transfer between phases, the miscibility, source and sink terms, the compressibility of the phases, and hysteresis and thermal effects. Although we are trying to address such problems in a current working in progress. So some basic notations, the standard one, the porosity of the porous medium phi, and capital K is the permeability of the porous medium, Si is the saturation, the viscosity, little k is the relative permeability, Pi is the pressure, Rho is the density, Pij is the capillary pressure, and G is the gravity number. So we start from the base for the basic mass balance equations for each phase as standard. Again, the key issue here is the relative permeability and the capillary pressure. We use the traditional classical Darcy-Muscat extension for multi-phase flow, and we consider static relative permeability in the position of dynamic relative permeability, in which in turn also includes hysteresis phenomena. Here we consider the core model, since for this particular case we have some kind of analytical solutions in which we can compare some of our results. But we are using such methodology to a more a general class of quadratic models, jointly with the work with Castaneda, Marchesin, and Furtado. So in the real-world experimental relative permeability measurements is like this, as usual. Everybody knows about this. And this can be time-consuming and very uncertainty. And to the case of three-phase flow, the determination of the endpoint is such a mess. Even to the case of the core model, if you go to the zero-slope behavior like this, you have a so-called transitional shock waves. If you go to the positive slope, you can remove such kind of behavior in the model. So we need to develop some kind of numerical technique that handles simultaneously such both situations, since in real we have both possibilities. It's at least to me, it's quite hard to argue that this reach this 0 point with zero behavior or positive behavior. And we also consider two static capillary pressure, but some people are working with dynamic capillary pressure, at least for two-phase flow. Is a very brief list of people who work right now on the dynamics of capillary pressure, no equilibrium models. This is the typical behavior of the capillary pressure in real application, and this is our model that we consider. We use the hypothesis of Aziz-Sitari in order to express the three-phase capillary pressures in terms of the two-phase capillary pressures. So we use an extension of work of Douglas and Pereira for two-phase flow, just to mimic the behavior, the qualitative behavior of the capillary pressure. This is, of course, idealized model. So we also consider unsaturated porous media. Here is the phase mobility, is the relative permeability and the viscosity. The total mobility is the sum of the individual mobilities, and as usual, the fractional flow functions, as before in the previous talks. So we can reach with some manipulation to this fully coupled system of equations. Is a convection diffusion system coupled with elliptic equations. And we use the phase formulation, since for such formulation, we do not care about the form of the relative permeability, at least in a first instance, the form of the capillary pressure, and since to the form of the relative permeabilities and the capillary pressure, since they are functions of the medium. And as mentioned before, the functional form of the relative permeability can affect, for instance, the existence of a global pressure for the case of two-phase flow. So the computational method, this is the scheme. This is the full system of equations under appropriate boundary conditions. Here we select the water and gas saturations and the oil pressure. We use operationally splitting approach. The basic idea, as discussed before, is to decompose the full set of equations in order to get some smaller problems and then solve each one with specialized techniques. Here we have a list of some works with a very sharp analysis of these time-splitting errors, just to support our choice. So the basic idea here is, for each time step, we solve these three problems sequentially. We solve first the elliptic equation, given initial saturations. We can solve the elliptic equations for the oil pressure, and then recover the total velocity. And then we can use the total velocity computed in this stage here, even with an extrapolation, if in a computational point of view, to solve the convective transport for one time step. And then finally, for the same time step, we use the solution of the hyperbolic system as an initial condition to the diffusive problem. So this is the way that we decouple the equation and how we solve it sequentially. So how we handle the numerical approximation for each problem. The idea is design an approximation in which handle the especially varying flux functions at the interface, and the discontinuous and the capillary pressure that in this work is discontinuous at the interface. So let's start to the case of the hyperbolic system. Our choice is a central lax Friedrich scheme, but let me try to explain why I'm using such approach. To the case of mixed hyperbolic parabolic diffusion equations in heterogeneous medium, it may be necessary to design nonlinear transmission condition in order to capture the correct solution. This is quite well documented in the work of Andreanov and Clement-Cancés. They perform a rigorous analysis, mathematical analysis and numerical analysis, and to the case of two-phase flow with gravity, if you neglect the diffusion, you may not compute the correct solution, even to the case of two-phase flow. And here, they design a strategy that is based on upwinding, phase-by-phase numerical scheme developed originally by Chavan. And here we have two options. Or you solve the full set of equations, the convection diffusion equation, or if you solve the purely hyperbolic equation, you need to come up with a coupling condition that captures the effects of the capillary pressure. So they perform a rigorous analysis, and they solve a purely hyperbolic set of equations plus a nonlinear coupling condition. So I met Cancés in 2002 in the HYPE meeting in Padova, and we tried to extend such technology to the case of three-phase flow. And our first study revealed that we need some kind of well-suited capillary pressure in the same spirit of the total differential condition to the global pressure to the three-phase flow. We need some kind of restriction, some constraint under the capillary pressure in order to derive some kind of coupling condition to the case of three-phase flow. This is not surprising since Professor Marchesin, to the case of three-phase flow in a homogeneous medium, the diffusive effects affects the selection of the correct waves. And this is not so surprising that this also happens to the case of two-phase flow to the case of the gravity. So I tried other options for some colleagues, and I found something that, okay, to the case of central schemes in a kind of semi-discrete formulation may fail to the unique entropy solution, to non-convex conservation loss. And to the case of three-phase flow, the semi-discrete scheme proposed by Kuganov and Tadimor may lead to oscillations to the three-phase flow. This is related to the way you calculate the velocity at the interface. And it's quite hard to find some kind of rigorous analysis for semi-discrete central schemes, or like DG, SSP, strong stability preserving Runge-Kutta schemes for this kind of equation of conservation law with a discontinuous here. So, but on the other hand, Carlson and Towers provide the first convergence proof to the case of nonlinear scalar conservation law, precisely of this form here. They prove convergence to the unique entropy solution. And based on that, and additionally for some other results, given some numerical evidence that indicate that the structure of the lax Friedrich scheme is somewhat well-behaved to discontinuous flux functions. And they have some kind of, in Carlson and some others, and Burgess and Towers they worked a lot in the last decade to the case of conservation laws with discontinuous flux functions. So, based on that, in the past, I worked with this kind of scheme here, and then the basic idea here is just to combine the same framework of Nassier-Hall-Tadmor and this rigorous analysis of Carl-Centaurus to design a scheme to this kind of equations. This scheme is basically the Nassier-Hall-Tadmor schemes in terms of implementation. And the idea here is, this is the position of the fluxes. You have the cell here in an original grid, the cell in the original grid, and the scheme is in a staggered grid. So the flux is posed here and here, and the discontinuity is here. So the case of the hyperbolic problem, there is no kind of coupling condition. So we can avoid this. We take advantage of the natural staggering of the central scheme to avoid any kind of coupling condition here. This is for the hyperbolic part. To the case of pressure, velocity, and parabolic equation, to the case of to the elliptic equation, we use Harvey-Atomar spaces, somewhat following the work of Professor Douglas and Professor Felipe Pereira to such kind of problems, and we use some kind of fixed point procedure in an iterative procedure. And to the case of parabolic equation, we use the same methodology based on the same works, heavily based on Porous and Douglas, that I will try to explain why I'm using such a methodology. The idea is how to handle the discontinuity of the capillary pressure here. So just let's consider two subdomains. So we have the interface here. So we have 3 degrees of freedom. We have a hidden state here that leads to some kind of continuity of the flux. And following Porous and Douglas, this is the Hobby transmission condition, somewhat well known. And following a dimensional analysis, we can look to this coefficient here that they found to be like this, in which this is the somewhat of effective diffusion. This kind of harmonic mean comes out naturally from the mixed finite formulation. And according to Douglas, this quantity must be positive. But if it's positive, you cannot handle the degenerate case of diffusion. Like we have some problem here, of course. And this is something that I found, but I don't know if it's a stupid idea, just some kind of interpretation. If you write this condition here, for the sake of simplicity, we use some very simplified notation and define beta exactly as this quantity that is the same that appears on both sides. We can formally write by this way, this Hobby transmission condition. And if you remember the Rankine-Goniot condition, this reads precisely by this way. And of course, you can manipulate quite easily the Haubrink boundary condition and can reach by this way here. It's something different for me. I haven't seen exactly this kind of interpretation. And it fits to the Rankine-Gugnot condition that somehow, if you look to the parabolic equation as a modified conservation law, in some way, it seems that the continuity of the flux satisfies some modified Rankine-Gugnot condition. Of course, this needs to be more, to go deeper in this issue. This is just a guess. And this leads to a naturally the same fundamental interpretation to the case of zero velocity. In the case of the gravity, you have a stationary wave, and you have the continuity at the fluxes at the interface, precisely as in the case of the Rankine-Gugnot condition. I don't know if there's some kind of more rigorous explanation to the possible connection between Haubrink transmission boundary condition and the Rankine-Gugnot jump condition. Okay. Let me show some numerical experiments based on this. This is the boundary initial condition, no flow on the top, on the bottom, injection of water and gas on the left, and the production of oil and water and gas on the left, and the pressure is kept fixed here, following the advice of Furtado and Pereira in order to capture viscous fingers effects, but I'm not dealing with this problem here. This is a random field, courtesy of Furtado and Pereira. This is a random relative permeability field. So this is the range between the maximum and the minimum values of the absolute permeability. Here on the top this is the ratio, and on the bottom, sorry, this is in the top, and in the bottom is the ratio. And what we have done here is I perform longitudinal cross-section and then lateral projection with under scaling, just to put in this framework here. And on the right, it is the results of Professor Marchesin to the case of no gravity here. We have this Buckley leveled shock wave, the transitional shock wave, and the composite wave here, the small shock and the rarefaction. And on the other hand, with discontinuous capillary pressure with gravity. I used this as a perturbation of the free gravity case, since I have no idea of Riemann solutions for the case of three-phase flow with discontinuous fluxes. And at least to me, it seems that the structure of the solution is present. Here we have the fluctuations since I took the longitudinal section precisely at this position here. Here, 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 and here. This is the case of higher constructs of the heterogeneity. And if we go back and forth, it seems like a scaling of the structure of the solution. But again, I have no idea if in fact it works. But to me, it seems like a scaling. You can go. I know that Professor Felipe and Furtado has some kind of results for the case of two-phase flow, but I don't know if the same ideas can be extended somehow easily to the case of three-phase flow. This is the subject of my PhD, supervised by Professor Pereira. I'm trying to get some idea. This is the same for the case of the gas, the same behavior, the structure of solution to the case of discontinuous capillary pressure seem to be present. Here is, again, the case of a two-phase flow, but the discontinuity now is induced by the hysteresis parameter. You have two kind of curves here, and the same definitions. We have the same type of system of equations here. We have two fractional flow functions, and of course we can have discontinuous fractional flow functions, precisely as before, with distinct flow regimes here, the case of gravity and gravity. Just to have an idea, no gravity here. And here have gravity, have the cross of the fractional flow functions. We try to develop some kind of extension of Orleans constructions to the Riemann problem, to this kind of problem. And here is, we get, without gravity, the classical Berkeley-Leverett solution. And here is the same solution, basically, the same convex hull construction. In orange is the analytical solution, and in dashed line is our numerical solution. We do not use some kind of very fine mesh here, but we had the correct solution. And so based on such construction, we extend to balance law models with an interface. We use the Euler equation as a model problem, since with high friction, there is an intricate connection with the parabolic Darcy-like equation, as found by McCarthy. McCarthy found the one-dimensional Darcy law as a limit of the compressible Euler equations. He's not suitable rescaling. So this is the basic Nassier-Routhard-Moore scheme, and we properly derive such predator-corrected scheme that handle the source term here, that can be stiff. We use 3 test cases to finish with gravity and friction. This is Chalon's works. This is made in a Goodenough type scheme on the left. On the right is our scheme. And they use, as you can see here, very fine mesh. And we use a basic scheme in a laptop, and quite fast. Is the pressure. On the left is their solution. On the right, our solution. As I mentioned, with 1,003 seconds in a standard laptop. I have no idea of the time that I did find the numbers in their papers to compare the times, but our time is quite fast, I think. Here's another problem based on gravity and friction for Euler equation from Kokel and Gondolewski. Here's their solution. I always forget. Oh, the density. Here's the density. Here. And here's our solution. Here's 0.8. Here's 0.8. I need to make a better figure here. Here's our solution to the velocity. And here's to the, let me see here, to the pressure. And just to finish, we have coupling with the hyperbolic and a balance law, since we have this factor here that appears here and here, and for less than 0.25 is 0, and for greater than this quantity is this value here. So we have a hyperbolic equation here and a balanced law equation here, and they derived a scheme with a coupling condition. In our case, we do not use any kind of coupling condition. We just run the scheme and treat each case in the same way, without any kind of coupling condition. This is the same for other kind of equation of state to depression. So, shortcomings, I think we need to improve the mathematical analysis and some kind of convergence analysis for such approach. And I thank for any kind of help of the audience. Thanks a lot for your time.